Hello everyone, my name is Peijie. In this video, I will present gScoreCAM, what is clip looking at? Work by Peijie Chen, Qi Li, Seth Bias, Trim Bill, and Anne Nguyen. Foundation models, such as OpenAI's clip, is powering many downstream tasks, from visual question answering, text-to-image synthesis, to image editing. But the inner workings of clip are still largely unknown. For example, OpenAI found that clip can be fooled by typographic attack. Putting a small piece of paper with text written on it will change clip's prediction. Here, from Granny Smith to iPod, or chestnut to piggy bank. But what makes clip change its prediction? One common technique for gaining insights is to visualize saliency or attention maps. For instance, clip thinks this photo highly matches the prompt tennis racket. But what is clip actually looking at? Yet, state-of-the-art CNN-based and VIT-based methods often generate noisy heat maps covering many objects. Perhaps it is due to clip being so sensitive to many visual cues. In this research, we ask, in a complex many-object scene, which objects are important to clip? To answer this question, we propose gScoreCAM, a saliency method for clip. gScoreCAM works as the following. For an input text-image pair, we first pass them to clip and extract the activation maps at the last convolutional layer of the clip's image encoder. We take only the top 300 highest gradient channels and upscale them to the input image size. After that, we mask the input image with selected channels to obtain 300 masked images. We pass these 300 masked images back to clip and obtain important scores for the channels. Finally, using the important scores as coefficients, we linearly combine the channels into a single clip heat map. The original ScoreCAM uses all activation maps, which often results in a very noisy heat map. Instead, gradually removing least important channels reveals the most important object, here the tennis racket, that contributes to the clip's decision. In another complex scene, shifting focus away from text and random objects, our method correctly localizes the black backpack. We test our method on Zero-Shot Object Localization using clip on 3 different datasets: ImageNet v2, Microsoft COCO, and PartImageNet. Like ImageNet, ImageNet v2 often contains one single object per image. In contrast, COCO images often include multiple objects of different sizes at various locations, which makes localization more challenging. PartImageNet is a fine-grained version of ImageNet, where object parts are labeled. So the task requires fine-grained localization of, for instance, the fish tail or the fox legs. On ImageNet v2, ScoreCAM and our method are the best. On COCO and PartImageNet, our method is about 1.5 to 3 times better than many methods and slightly better than ScoreCAM. In terms of runtime, our method is 10 times faster than ScoreCAM in theory and about 8 times faster in practice. But what makes our method achieve the best scores on COCO and PartImageNet? Our method is better than others when the testing images includes many different objects. For example, here there's a dog, a plate, food, etc. Yet, our method can accurately localize the potted plant behind the dog. In contrast, other methods often highlight too many incorrect objects. Similarly, we correctly localize the laptop under the chair while other methods failed. When asked to localize parts of a random object, our method is the most accurate, here finding the tiny head of the king snake, or the head of a bear, or the foot of an Arctic fox. So, how can our method help with understanding clip? gScoreCAM enables us to discover that clip can read text, and it interestingly prefers text over visual cues. For example, if an image contains both microwave object and the word microwave, clip will select the text instead of the object. Similarly, Here, Clip will choose the word bicycle over the actual bike. Going back to the typographic attacks examples earlier, using gScoreCAM, we find that Clip can read the iPod text, localizes the apple, and even the background fence. Similarly, Clip can localize the chestnut seed, the dollar sign, and even the hand holding the chestnut seed. gScoreCAM also shows us bias in Clip. For example, it tends to think programmers are white men, while janitors are black men. A worrisome bias that may cause harmful consequences when Clip is used in many real-world downstream applications. In sum, we propose gScoreCAM, a state-of-the-art localization method for Clip on ImageNet, COCO, and PartImageNet. gScoreCAM performs comparably to ScoreCAM, the best prior art on zero-shot object localization using Clip, but is about 8 times faster than ScoreCAM in practice. gScoreCAM is approximately 2 to 4 times more accurate than other methods excluding ScoreCAM on ImageNet, COCO, and PartImageNet. In particular, our method performs better in more complex cases, that is, localizing an object in multi-object scenes, or localizing a part of an object. This research was funded by the National Science Foundation, Open University, and Adobe Research.